In data science, performance matters, and it matters a lot. Whether you're simulating dice rolls or analyzing millions of records or trying to simulate some scientific models, loops over Python lists will not cut it. And this is why we use NumPy, because it has this edge when it comes to performance and speed. But let's actually measure the difference. Here I'm gonna use a Jupyter function called timeit. This is not a standard Python language thing. It's only in the interactive Python kernels or in the IPY kernels and Jupyter notebooks. So let's see how that works. I'm gonna import the library random. And using list comprehensions, I'm gonna generate a list of all the possible outcomes for a 6 million times that we roll a dice. So to do that, we're gonna use the random function or the rand integer, and we want that integer to be any value between 1 and 6, which is the number of faces we have on a dice, for underscore in range of 6 million. Notice the underscores here are ignored. If I run this, it will take a second, but then we get all the 6 million times that the dice has been rolled. Now, we don't really care for the numbers, but we really care for timing it. So I'm gonna add this magic directive. So if you add the percentage sign and then the word timeit and you run this again, we'll just give it a second to execute. And once it's done, we'll see what we get. All right, so what this line here means is that on average, this takes 1.5 seconds plus or minus 27.3 milliseconds. How did it actually go about making this math? It actually executed this line 7 times. In each one of those times, it only ran one loop, and the average of those 7 times were 1.5. Now, what is the one loop here means? Let me try to do this one more time using something that's a little bit more simple. So timeit, and we want to time how long does it take to perform this mathematical operation, 1 plus 2. If I run this, obviously, this should not take 2.2 seconds, but what actually happened here is that it executed this statement here 100 million times in 7 runs. So in each one of those runs, it executed this line 100 million times just so that they can get a number large enough that they're able to measure. And based on that, they've concluded that this takes 2.79 nanoseconds plus or minus 0.124 nanoseconds per loop. So this is how you know how fast your code is. Now, this is not a video on timeit, so I'm gonna take this cell off and let's try to do the same thing only with NumPy this time. So I'll timeit, and we'll use the NumPy random integer function to generate numbers between 1 and this time I'm gonna do 7 because in NumPy the rand int actually is exclusive of that last number, and we want this array that it will be generated to be of 6 million records. Let's run this and see how long it will report this took to execute. So it is 40.4 milliseconds compared to 1.5 seconds. Why did it run this code 10 times in each one of those 7 runs? Is because it was small enough that it needed to run them multiple times just so that they can get the number to be large enough to be able to measure it accurately. So let's try it again with 60 million this time. Now I'm gonna do the same over here, and I know this will take a second, so I'll pause the video and I'll come back in a bit. All right, so Python ran 7 runs of this, 1 loop each, and each one of those runs was 14.9 seconds on average to execute this function here. So yes, it says 1 minute and 59 seconds here. That is not how long it took. It's how long it took Python to execute this function 7 times, because they're trying to get the average of how long these function will take. Now I'm gonna do the same thing with NumPy. This time I'm not gonna speed up the video because I don't think it will take that long, but let's go ahead and see that. Here we go. It is done in 400 milliseconds. 7 runs of this, and it was able to conclude that this on average takes 400 milliseconds compared to 14.9 seconds. That's a dramatic difference between the two numbers here. So this is where NumPy shines. It's when you have large data sets. This is why we use NumPy in our data science and data analytics work. NumPy is not just cleaner code. It is orders of magnitude faster than regular Python lists. This is why whenever there is a data-heavy project or there is a data-heavy field, you'll find that it relies more on arrays than it does on plain Python lists. Now that we know that arrays are fast, let's see how we can run some mathematical operations on them.